Hello everyone! So here is section 1.3 video, more on functions and their graphs, a little bit further into information that we can gather from functions and their graphs. We're going to talk about intervals that are increasing and decreasing. We're going to talk about where we can find relative maxima and minima. Man, we're going to do a ton. We are going to test for symmetry on functions and evaluate piecewise functions. So hopefully some of that rings a bell. If not, we are going to touch on it and learn about it today in this video, okay? So let's get started. The first thing we're going to talk about here is increasing and decreasing and constant parts of graphs, okay? So take a look at this. Graphs and math, we kind of sometimes get into random numbers, and random graphs, but it's easily applied to the real world. Check out, here's a graph of the average fuel efficiency of new United States passenger cars. So it goes down, it kind of stays the same, it goes down, it shoots up, and then it keeps on going up, okay? So it varies, right? Graphs don't always stay the same. So when this happens, in math, we describe it as increasing, which happens when I have a positive slope and I'm going uphill. It's always from left to right, so always keep an eye on that. This is how I remember it. Uphill, decreasing, left to right, it goes downhill, it's falling. And constant is when I have a horizontal line. Okay, so we want to make sure we know that this is how those three things look on a graph. Okay, when we describe things that are increasing, intervals that are increasing, decreasing, or constant, we use interval notation just like we talked about in 1.2 with domain and range. Okay, but the biggest difference now is when, no matter whether we're talking about increasing, decreasing, or constant, we always, guys, use the x values, okay? We're always looking, notice how they say left to right. We are always going from the smallest, the least x value to the greatest x value, okay? Some reminders of when to use parentheses or brackets. Notice I also added something in here when it's included in two intervals, okay? I can't say a number is increasing and decreasing at the same time, right? Just like I can't be in two places at once. So when that happens, the way we get around it in math is by using parentheses. So add that to your notes, when to use which type of notation, okay? Parentheses and brackets. So let's take a look at these two examples here, and that's what we're going to do to practice, okay? The first one here, we go through, I kind of just look left to right, I start to look at it, and I say, okay, what is happening from left to right first? Oh, notice how I just drew that. I'm decreasing first, okay? I'm going downhill. This arrow goes upwards and outwards, okay? So remember, in interval notation, I'm always talking about the least x value to the greatest x value. So this is telling me this is going forever in this direction. So what is my least x value going to be? Negative infinity. Yep. So it's decreasing from negative infinity to when? When does it stop going downhill? Right here, right? It stops going downhill right about here. And what is that? That x value is 0. Awesome. And then what happens? It kind of turns around. Right now I'm increasing, starting at 0. Notice I have a number in two places at once, so I have parentheses. And I'm up, 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 going increasing until about here at 2, we'll say. Okay? And then what happens? I start to go back down, right? And the way we use that and, we use this u saying and, I'm also decreasing from 2, okay? Then I'm going down forever. Notice I'm not interested in the fact that I'm going down in the y direction. What's happening to my x's when I'm going down and out? They're getting bigger. They're getting closer to infinity. Okay, so there's my end of my decreasing unit. I'm increasing just for a little bit, right? 0 to 2. And then I'm decreasing over here from negative infinity to 0. And then I'm also decreasing from 2 to infinity forever. Don't get confused that I do know, I notice that's going down, right? And you guys are probably thinking that should be negative infinity. It would be negative infinity if I was working with y. Totally, that's going down in the y's. But my x values, which is how we write this in interval notation, is going positive. It's increasing in the positive infinity direction. Okay, let's talk about this next one here. Increasing, where does it look like I'm increasing? I am increasing in this area, right? Starting here, and then I'm going up. So starting at the x value of 0, it's an open circle, so I have a parenthesis, and it's going up and out. What's my x value if I'm going up and out? Forever, infinity. Okay, there's my increasing. Am I ever decreasing? Do I ever go down? Never. What is this first part called? That first part, like we could say NA, that first part is my constant. So how long are we constant for? Well, I have that arrow, right? This arrow says forever in that left direction. So from negative infinity all the way up until 0, my x value of 0. It's a closed circle, so I use a bracket. Okay, so that's how we talk about increasing and decreasing using interval notation when we're looking at a graph. Let's talk about relative max and min. So when we increase and decrease, we create these little tiny peaks, right? And these little mountains and these little valleys, which we call relative max and relative min, okay? It may not be, this is a maximum, but it's not the highest point on the whole graph, right? This is a min, but it's not a min for the whole graph. That's why we call them relative. Just in terms of where I'm peaking and decreasing, my increasing and decreasing, we have created maximum and minimum points. Okay, so let's take a look at this example. I notice right here I have a peak, right? I have a maximum. And how we want to write this is we want to say what x value does this happen at? So the x value is at 0, and I'm going to say f of 0, right? Instead of f of x. When my x is 0, my y, my maximum is 6. And that's my relative max. That's where my max happens. My relative min, where do I have some valleys down here? Okay, when my x value, we'll round and say that's 3. Okay, f of 3. And my min, what is my min here? We'll say that's 1.5. Okay, that is how we want to write our max, relative max and min. Add the x values. What is that y? Max, what is that min? Y. Okay, great work, guys. We're going to talk about one more thing in this video. And the next thing we're going to talk about here is symmetry. Now we see symmetry all over. Check out these great photos. This dog, we would say, has y-axis symmetry. Notice that y-axis, that vertical line right down his face. Symmetry, we know if we fold it in half, it would be the exact same, okay, which the shepherd does have. Notice this photo has a horizontal x-axis symmetry. If I folded it in half, the reflection of this symmetry would be right on top of each other, right? It folds right on top. It's symmetric across the x-axis horizontally. Now this happens with graphs, right? I can fold this graph right on top of each other vertically on the y-axis, and it would have symmetry about the y-axis. That's what we would call it. Here, if I folded this graph downwards, right across the x-axis, I would say it's symmetric with respect to the x-axis. Notice this one, if I flipped it, reflected it downwards once, right here, and then again, it would rotate here, and that's when we call something that has origin symmetry. When we flip it downwards and then over twice, right? Flip it once and then again, and it lands back on itself. That is when we have something called origin symmetry, okay? And we need to be able to test for this, not looking at graphs, but looking at equations, okay? And here are some rules. When we want to test, and you want to make sure you have this in your notes very, very clearly, when you want to test something is symmetric about the y-axis, how do you do it? What you need to do is substitute negative x in for x and solve the equation, simplify the equation, and if it equals the original, then hey, it's y-axis symmetric, okay? If I want to test something is x-axis symmetric, what do? I need to substitute a negative y in for my y, simplify it, and if it equals the original, it's symmetric about the x-axis. Okay? And if I want to determine something is symmetric about the origin, I need to substitute a negative x in for x and a negative y in for y. Two things there. And then if it's equal to the original, I'll know it's symmetric about the origin. Now these rules come from the graphs. Notice what happens. This point x comma y reflects over here, and the negative x, that's what it changes to. It changed from a positive x to a negative x. That's why we substitute a negative x in for y-axis symmetry. And the pattern follows. So if you're interested in why these are the rules, just check out these graphs. Okay, now we're going to practice this symmetry rule with this example here. Okay, so I copied and pasted those directions, those rules, which we want to make sure we have in our notes. And we want to determine, we want to determine whether this graph is going to be symmetric with respect to the y-axis, x-axis, or the origin. So we're going to go ahead and test each of these. Okay, first let's test y-axis. So in order to test something is symmetric in the y-axis, okay, what do I have to do? Substitute negative x in for x. So let's go for it. I take this x and I substitute in a negative x. And that's all. There's no simplifying that I can really do. Okay, and then I just compare. Okay, and it says if this equation is equals the original, then it's y-axis symmetric. Are those two the exact same? No, right? They are not. So it is not y-axis symmetric. So now let's test for x-axis symmetry. So in order for me to test x-axis symmetry, we need to replace the y with a negative y. So let's go ahead and do that. So I have x equals, I put that negative y in, squared minus 1. I simplify. Guys, negative y squared, negative y times negative y, gives me a positive y squared. And again, I'm done simplifying and I compare. Is this equation equal to my original? Well, yes it is, right? Notice they're the exact same. So far I can say that this graph is x-axis symmetric. If I graphed it, it would be symmetric with respect to the x-axis. And I can also test the origin. Remember, the origin is what happens when I replace the x with a negative x and the y with a negative y. When I simplify it, I can't simplify the negative x at all, but the negative y squared becomes a positive y squared. And when I compare this new equation to my original, again, it's not equal. Not equal. So we can confidently say when they're the same, in this one, it is x-axis symmetric. Okay, guys? Great work. There's going to be a short video that follows this that you guys are going to pop on. You guys rock. Good job.